Hello and welcome to the next video in our Essential Skills series. As you know by now, these videos are covering the skills which are essential to prepare you for paper 1, the matric physics paper. I'm Dr. Derek Fish. I've been director of the Unizulu Science Centre at the University of Zululand for the past 30 years. In your booklets, this will take place on pages 62 to 65. And this video will look at electrodynamics and alternating current, but specifically the equations which have to be solved. I must remind you that these videos are not intended to cover all the coursework. That needs to be done in class. This is revision and preparation for the exams by focusing on essential skills. Before we get to pages 62 to 65, I want you to turn to the front of your booklets to page 3. And let's look again at the contents page to see where this fits in. Remember, the contents are arranged by our 4 skills: graphs, free body diagrams, equations, and ratio questions. Under the equations section, if I expand it, we're looking at the section on electrodynamics and alternating currents and how to solve the equations associated with question 9 in the matric paper. Once again, a comment from the examiner: learners still cannot work with scientific equations or formulae, so it's important for us to get on top of these. If you haven't done it, please make sure that you've watched the initial video on equations introducing the progress method. On page 4, let's see where electrodynamics fits into the curriculum. It fits obviously under the electricity and magnetism section, and right at the end, in grade 12, you'll look at electrodynamics, which look at electrical machines like generators and motors, and alternating current. Notice again, there's a graphs application, another of our skills, comparing potential difference graphs for alternating and direct current. In the exam, electrodynamics, motors, and alternating current is always question 9, and on average over the last 3 years, it has been for 12 marks. Here's a comparison of exam questions for the last 3 years, November 2018, 2019, and 2020. The questions have been very similar. There's a first part, which is some basic questions about either a motor or a generator. And then there's a second part using the equations to do an alternating current calculation. We'll look at all these questions very carefully at the end of this video. So the first part is normally 5 marks. And it's really some quite simple questions about generators or motors. Again, we will come back to this at the end of this video. Let's look on page 5, what skills are required for this section. Again, because graphs are involved, all of these graph skills under skill number 10 are important. And a reminder of the examiner's comment that a severe lack of skills was evident when marking matric papers. So let's make sure that we develop those skills, not just for this section, but for every section. What sort of graphs are involved here? If you look on page 6, we reminded you that graphs could represent the rate at which things happen, the relationship between variables, and a visual representation of the data. Now, the graphs you'll deal with under alternating current are rate graphs. In particular, they are sine graphs. They show an alternating current or voltage which goes from positive to negative, and that voltage or current is graphed against time. So get used to these particular types of graphs. So before we get to the equations for electrodynamics, let's have a look at some of the basic theory. But again, a reminder that you should use this video after you have finished this section in class, and you should refer to your notes or your textbook for a full coverage. So what do we need to know about? Well, you should know by now that a generator produces alternating current, or AC, which changes direction many times per second. In household electricity, it changes direction 50 times per second. And that's because of the coil or the magnet, whichever is being turned, turning through 360 degrees. And this causes the current to change direction. Now, sometimes it's difficult to see this just from pictures in a book. And once again, we'll go to a fantastic PHET simulation. This is called Generator. Reminder to the teachers that the simulation is in your teacher pack. And I encourage you to spend some time playing with it yourself and learning as much as you can about generators. But let's see what we can learn from this simulation. So this is a great way to learn about generating electricity. Start off with the bar magnet. And of course, as we move it around, you can see the magnetic field indicated by the small and the large compass needles. Now, if we have a bar magnet like that near to a coil, when we move the magnet in and out of the coil, it can actually generate some voltage as that magnetic field passes through the plane of the coil. If I replace the voltmeter with a bulb, you can see as we push it in and as we pull it out, it generates some electricity. What you would have noticed from the voltmeter, as we push it in, we get a negative voltage. As we pull it out, we get a positive voltage. So you see how the voltage alternates or changes direction, just like that. Now, of course, we can make this into a generator. And if we have some sort of source of power, it might be a coal-fired generator, it might be one run by petrol, it might be turned by hand, or in this case, we have water falling on a water wheel that turns a magnet, and that changing magnetic flux through the coil causes a voltage to be generated. But you can see that even though a bulb would keep shining, the voltmeter changes from positive to negative as the north or the south pole passes. By the way, one of the things we can show quite nicely here is the three things which will cause a generator to produce a higher voltage. The first thing is if we let the water run very fast, it's now spinning at 84 revs per minute, and you can see we're getting a higher voltage. If I turn the water right down to 24 revs per minute, you can see that the voltage is lower. So first of all, the speed with which we change a magnetic field is important. Second thing is the number of coils. We've got 3 coils here, and you can see, watch the voltage or the maximum voltage as I go down to 2 coils and 1 coil. And you can see that the more coils we have, the greater the voltage which is generated. The third thing is we can change the strength of the magnet. If it's a very strong magnet, you can see the peak voltage is quite high. If it's a weak magnet, the peak voltage is quite low. So those 3 things, the strength of the magnet, the speed with which the magnet is moved around or in and out of the magnetic field, and thirdly, the number of coils. Now, alternating current is useful, particularly when we want a transformer. And you can see we've got 2 coils here, a primary coil with alternating current going through it, and a secondary coil. If we move it closer, especially if we move it over the primary coil, you can see that it induces an alternating voltage in the secondary coil. So that is quite useful. But if we actually change our source to a DC source, you can see there's no, unless we actually move it in or move it out, but if it's just stationary, because the magnetic field is not changing, there's no change. Now, transformers are very useful for changing voltage up or down. So your cell phone charger changes the voltage from the mains of 220 volts down to 5 volts for your cell phone. In a car, the coil changes the battery voltage of 12 volts up to 30,000 volts in order to make a spark in the spark plugs. So I hope that was helpful in helping you to understand just how generators convert mechanical energy into electrical energy. Perhaps you're still not clear about the difference between alternating current and direct current. So we're going to go to another great simulation from PHET. Again, teachers, you have this. And this is the circuit construction kit, which allows you to build both AC and DC circuits. Now, it's really easy to put a circuit together, just like I've done here, by dragging components onto the work area. And you can see I've set up a basic circuit with a switch, a power source, and a light bulb. On the left, we have an AC power source. On the right, we have a battery or a DC power source. Let's see what we can learn from this simulation. So let me switch on the switch on the AC side, and you can see the bulb lights, but you can see the electrons are alternating in direction. It's very slow here. In our household electricity, they alternate or change direction 50 times every second. When I switch on the DC side here, you can see that the bulb is glowing. The electrons are all flowing in the same direction around. Now, we've got a voltmeter here. Let's connect it and measure the voltage. If we measure the voltage across the battery here, we get a steady 9 volts. Remember, whether the bulb is shining or not, it measures the voltage. So obviously no internal resistance here. If we disconnect it and connect it on the AC side, we find we have a problem measuring voltage because you can see it's changing all the time. It's changing from positive to negative. So in fact, that's not really a very good way of measuring voltage for alternating current. If we take our ammeter, we've got a non-contact ammeter here. We put it over a wire. You can see it's measuring a steady 0.9 amps in the DC circuit. If we put it over a wire in the AC circuit, again, it's difficult because the current is changing, and so it's difficult to read it that way. So what's probably better is to actually bring out a voltage chart. And this voltage chart measures voltage against time. So let's connect it up to the DC circuit. And we can, I think I've got the polarity wrong. Let's get a positive voltage. And you can see we're getting a positive voltage of 9 volts. If I show the values, that is a 9-volt battery. These are 10-ohm bulbs. So it's a steady positive voltage of 9 volts. Let's connect it on the AC side, and we see something quite different. We see a voltage that varies over time. And you can see here that sine wave, that the voltage goes from a maximum positive of +10 to a maximum negative of -10, and it varies over time. Similarly, let's have a look at the current chart. And this one we just need to connect. We can connect to any wire or even in the battery. You can see there's a steady current of just under 1 amp flowing in the DC circuit. But if I connect it anywhere in the AC circuit, again, you see this sinusoidal, like a sine wave, going from a maximum of +1 to a minimum of -1, and it keeps changing over time. So this is what we see when we draw graphs of voltage and current with an alternating current. We see a sine wave when we measure them against time. So I hope that was useful and that you understand alternating and direct current better and what sort of voltage outputs we get from them. So if you drew a graph of voltage or potential difference against time, if you just had a simple battery, we would get a straight line graph because it's a constant voltage that doesn't change with time. You would have seen graphs like this in video 4.2 on internal resistance. If you have an AC generator, because the coil or the magnet is rotating through 360 degrees, we get an alternating voltage or an alternating current. Now, on a DC generator, what happens is using a split ring commutator, it literally takes the negative part, the negative voltage, and flips it so it becomes positive. So this voltage is always positive. You can see the problem is it's got a big ripple on it, and in practice, capacitors or other circuit elements are used to make this a little bit smoother. So it's important for you to know the difference between DC and AC generators. You'll see that they look very similar. They have fixed magnets, they have an armature or a coil, they have some way of contacting between the coil and the meter here. Now you can see in the DC generator, you've got a split ring commutator. On the AC generator, you've got slip rings. Now, the function of these will be explained much more clearly in the next simulation. And as we've seen, DC generator gives you an always positive, or it could be always negative output, but it doesn't change from positive to negative. An AC generator gives you an alternating voltage. Now, again, it's difficult to understand this from simple two-dimensional pictures. So here's another great simulation. This is not from PHET, and it's not in the teacher pack, but the web address is here, and you can go to this. This is a great simulation which was done by Walter Pfent, and this will help us to understand the difference between DC and AC generators. Let's see what we can learn from this. So looking at the simulation, you can see we have a fixed magnet with the north pole above and the south pole below. I can add the magnetic field, and the blue lines indicate the magnetic field of the fixed magnet, which of course is unchanging. Here you can see our generator, and as we turn this coil within the magnetic field, we're going to get an induced current, which will be shown by the red arrows, and the black arrows will show us the direction of movement of the coil. So let's allow it. Sorry, one more thing. Notice we have a split ring commutator. So where the brushes are attached, the ring is split. So this wire on top will be attached first to one side of the coil and then to the other. And that will ensure that the direction of this current always stays the same, as we'll see if I start the simulation. So as the coil turns, you can see that the direction of the current in this top wire is either to the right or it's zero. It's momentarily zero when the brushes are on the split between the two sides of the commutator. You can see the coil turns in an anti-clockwise direction the whole time, but you will also see that the direction of the induced current in each side of the coils is changing. But because of the commutator, what you can see here is that the voltage is always positive. It never goes negative. Now, in a real generator, capacitor or some other electronics will be used to smooth that voltage to make it more usable. Now, at the moment, we're rotating it at 6 rotations per minute. I want you to try to imagine what will happen when we speed it up to 12 rotations a minute. Because in fact, two things will change on this graph. There's a change on both axes. So let me speed that up to 12 rotations a minute. And you can see, first of all, the period has changed. The wave has got much more squashed up in a horizontal direction. And secondly, Vmax has changed, because there are 3 things you can do to get more voltage or current out of a generator. One is to have a stronger magnet. The other is to have more windings on your coil. We've just got one here. And the third is simply to turn it faster. So you can see as we turned it faster, the period changed, but of course Vmax changed as well. Let's go back to 6 rotations a minute, and you can see Vmax is exactly half there. Let's pause this. This is a DC generator. And now we're going to change it into an AC generator. By taking away the commutator, now we have slip rings. What that means is this top wire is always attached to one side of the coil. So as the direction of the current changes in that side of the coil, so you'll see the direction of the current in this wire changes, and therefore the voltage goes from positive to negative. Just watch. So now it's to the right, and now it's to the left. Now it's to the right again, and so on. So you have a positive voltage and then a negative voltage. So this is an AC generator, and it's characterized by slip rings rather than a split ring commutator. Now, once again, let's consider what happens when we change the speed of rotation from 6 rotations per minute to 12. And just like before, you can see the period gets shorter. The frequency is doubled, the period is halved, and Vmax is doubled. So I think this simulation shows very nicely how the 2 different types of generators work. You can see the web address here, and I encourage you to go there and try out this simulation for yourself. So we've discovered that an AC generator takes mechanical energy in. One turns a handle, or it can be turned by water power or petrol. And what comes out is electrical energy. So mechanical energy is converted into electrical energy. But what would happen if you put 2 of these together? And in fact, we find that a motor and a generator actually really look very much the same. And if you connected the brushes together, if we turned the handle of the generator, mechanical energy would be converted into electrical energy. As that electrical energy goes into the motor, it would then turn the coil and we'd get mechanical energy out. So a generator simply converts mechanical to electrical, and the motor, which is really the same thing, converts electrical to mechanical. Now, of course, you get DC and AC motors just like generators. As I say, they look very similar to the generators, but the difference is, of course, here you're putting in electrical energy and you're getting mechanical energy out. Once again, the DC motor has a split ring commutator to ensure that it always turns in a constant direction. Otherwise, it would simply flip backwards and forwards. An AC motor, because the current is already changing, has got brushes and slip rings. So if the current changes 50 times per second, the motor would turn at 50 times a second, or 3,000 revs per minute. Now let's have a close-up look at a DC motor. And again, this is a great simulation from the National Magnetic Field Laboratory. And you can also follow that web address and explore it for yourself. So here you can see the different parts of a DC motor. There's a power source, in this case a battery. You've got wires and then brushes connected to the coil via the split ring commutator. In this case, there's just one coil showing, so it's easy to understand. But in a real motor, there'll be sometimes even thousands of coils. And then we have a magnet, in this case a horseshoe magnet. Magnetic field is always directed from north to south. And if I allow the motor to run, you can see that that electrical energy is converted into mechanical energy as the motor turns. Let me slow it down a little bit, and you can study what happens to the direction of the current in each part of the coil. Now, what we can also do is flip the battery around, so change the polarity of plus and minus, and you can see immediately the motor turns in the opposite direction. Now, these DC motors are becoming very important because, of course, electric cars are taking over from petrol-driven cars in many ways. So scientists are looking for really strong, efficient DC motors, which can drive our cars of the future. Electric cars have so many advantages over petrol or diesel-driven cars. Mostly there's no pollution, they are very quiet, they don't need a gearbox. When you brake, you can actually recharge the battery. And the search is on to find really efficient batteries so that electric cars can go a long distance. Now, again, this is just a very brief review of the content. And one other thing you'll need to remember are your left and right-hand rules. Now, it's difficult for me to show you on the small screen, but we have a left-hand rule, which is for motors, and a right-hand rule, which is for generators. Now, in each case, you need to put your three fingers at right angles to each other. And remember that your thumb is for the thrust or the force. Your first finger is for the field, the magnetic field, and your second finger is for the current. So remember, thrust, field, and current, all at 90 degrees to each other. And then you just need to get some practice in aligning them to the diagrams. For motors, you'll usually be asked in what direction is the force on the coil. For generators, you will be usually asked what is the direction of the current induced in the coil. There's some exam examples of these coming up. So, having looked at how generators and motors work and how alternating current is produced, let's consider some of the variables and equations that govern AC circuits. You'll find these equations and variables on page 62 in your book. So we've gathered that with alternating current, both current and voltage vary sinusoidally. What it means is they go up and down like a sine wave. That's the graph, and that would be governed by an equation like this. Now, don't worry too much about the detail. We could just replace that with the angle theta. Current will be the same, a sine wave governed by a very similar equation. In fact, with our household electricity, the frequency is 50 hertz, which means that the voltage or the current changes direction 50 times every second. Now, going back to question 8 and video number 4 in electric circuits for DC, if we have a simple circuit like this, there are 4 variables that we consider. There's the current measured by an ammeter in series in the circuit that's measured in amperes. There's a potential difference or voltage measured by a voltmeter in volts, which is placed in parallel across a circuit element like a resistor. There's the resistance. The value of the resistance is given in ohms. And finally, we might often want to measure the power in watts of this resistor when a certain voltage and current flows through it. Looking at these units, someone has suggested that this is a good way to consider this, that the number of ohms is the amount of squeezing that takes place, number of volts is the amount of pushing that takes place, and the number of amperes is the flow of the current. So maybe that's a picture which might help you to see what's happening. Now in electrodynamics, we want to take these four basic variables that we use in DC and extend them for the use as AC variables. So where we just have current with DC, we look at the root mean square current and the maximum or peak current. But it's the same basic unit, amperes, and the variable is very much the same. We'll explain this in a minute. With potential difference, we'll have the root mean square potential difference or the maximum or peak potential difference still measured in volts. Resistance stays the same. And in place of power, we'll talk about the average power measured in watts. Now, what do we mean by RMS or root mean square voltage and current? So here's a graph of a typical full cycle with a changing or alternating voltage. There's the peak voltage plus and the negative peak voltage. Now the RMS, the root mean square voltage, is that DC voltage, that steady DC voltage, which would have the same heating effect as the alternating peak voltage. Now in this case, in our households, we have an RMS voltage of 240 volts. The peak voltage goes over 300 and under minus 300 volts. Now, how do we calculate that? It's quite simple. The root mean square voltage is just the maximum voltage or the peak voltage divided by the square root of 2, and the same thing for the root mean square current. Now let's consider AC power. Power, of course, is always positive. It can't go negative, but it fluctuates. It changes with time. So how do you actually measure the power in an AC circuit? And it's most useful to consider the average power, which is just half the maximum or the peak value of power. So P average, the average power is half the maximum power. Now we should know that power is voltage times current. So it's half of Vmax times Imax. And you can write this as Vmax over root 2 times Imax over root 2. But of course, we know from the previous section that Vrms is just Vmax over root 2, and Irms is just Imax over root 2. So here we have the average AC power expressed in terms of the root mean square voltage and current. So this allows us to calculate power in an AC circuit, which is very useful. So for DC, remember we had Ohm's law, V equals IR. And we also had power equals VI, voltage times current. That's the power equation. Putting them together, we can get two more equations for power. E equals I squared R and P equals V squared over R. So these were covered in video 4 and they're on your data sheet. Now for alternating current, for Ohm's law, we have Vrms is equal to Irms times R. That's the AC version of Ohm's law. And that allows us to express average power in three different ways. Vrms times Irms, I squared RMS times resistance, or V squared RMS divided by resistance. Now you don't need to learn these because you'll find all of these in the equations at the bottom of page 39 on your data sheets in the exam. Let's have a look at that. If you go to page 39, this is what the data sheet looks like, and it looks like you've got twice as many equations as you actually need. In fact, we can get rid of those and those because those are just the Afrikaans language version, and we don't need them, and we can simplify it to say there are 5 important equations. One on IRMS and VRMS, and then your average power. Now, again, don't learn these equations, but make sure that you know how to use them. And the exam questions we're about to answer will really help you to know how to use these well. Don't forget, of course, that you have equations for electrostatics and for electric circuits, but don't confuse these. You also have your power equations here, but these are for DC, whereas the ones we've just looked at are for an AC circuit. So to try to help you understand those equations, let's look at some illustrative exam examples. Now, these are not in your booklets, so don't try to solve them, just follow on the screen. So here's one from the June exam in 2019. It's question 9 as usual. You've got a graph showing the voltage output of a generator and then various questions. So once again, graphs are important. This is a sine graph. It's showing 1.5 cycles. The full cycle actually ends at 0.2 seconds. It's a rate graph. It's showing how the potential difference alternates or changes with time. The first question says, does this generator have split rings or slip rings? Now, you should know by now that an alternating current generator has got slip rings, and that causes the potential difference to change like this. 9.2, which one of the diagrams, A or B, which they give you, shows the position of the generator's coil at time 0.1 seconds? Now, time 0.1 seconds, there's no potential difference being generated by the generator, and that is position B, when it's at 90 degrees, the plane of the coil, to the direction of the magnetic field. Finally, calculate the RMS voltage for the generator. Well, we need to start with the maximum voltage, which we can see there's 312 volts. And from your data sheets, VRMS is Vmax over root 2. So 312 from the graph over root 2. Simple calculation is 220.62 volts. Question 9 is usually quite easy compared with the other questions. So please don't run out of time and leave it out. Now, another illustrative question, also not in your books. This is from the KwaZulu-Natal trial paper, September 2020. Just wanted to show you that compared with other national papers, this was quite different. It was just a graph, no picture of a generator, and the calculations were all related to the graph. Let's have a look at it. So again, this is not in your booklet, so just follow on the screen. So here you had a graph when a coil is rotated in the magnetic field of a generator. This is the induced EMF, which you can clearly see is alternating. It's changing from +1 through 0 to -1. So that helps us answer 9.1. Which type of generator was used? Well, it must have been an alternating current or AC generator, because the current or voltage alternates, it changes. 9.2, which structural feature allows it to produce the above type? Well, it's the slip rings. I hope by now you know the difference between slip rings and a split ring commutator. 9.4, calculate the induced RMS voltage for the generator. Giving ourselves a bit more space. Well, we need to start off with what is the maximum voltage from the graph? It's 1. So Vmax is 1 volt just from the graph. And we know that VRMS is Vmax over root 2, which is just 1 volt over root 2, which is 0.71 volts. And we're going to need that in question 9.6. 9.5, a question about the time axis. It says the coil is now rotated at twice the original speed. Write down the period of the new wave. Well, the period at the moment of the original wave is there. Now, you can extrapolate 0.02, 0.04, 0.06, 0.08 seconds. So the old period was 0.08. If it goes twice as fast, the new period will be half of that. If you double the frequency, you halve the period. The new period will be 0.04 seconds. Remember, VRMS was 0.71 volts. 9.6 says calculate the average power generated if the generator produces a maximum current of 2 amps. Well, average power is VRMS times IRMS, just from our data sheet. And 0.71 we carried through from question 9.4. We multiply it. IRMS is just the maximum current of 2 amps divided by root 2. Do the calculation, and we get an average power of 1 watt. Again, that was quite a simple question, and I encourage you to make sure that you answer question 9. Now, it's your turn. We're going to look at 3 recent exam examples from the national final paper, and it's really important that you try these yourself before I give you the answers. So can I encourage you, please, to pause or stop the video here for 39 minutes. That's the total number of marks for these 3 questions, while you try to complete these questions on pages 63 to 65. I really hope that you did try these questions yourself. Let's go ahead and look at them. First of all, let's compare the 3 questions from November 2018, November 2019, and November 2020. And remember, as I said, question 9 is usually in 2 parts. There's normally a first part for about 5 marks with some basic structural questions about a generator or a motor. Then there's a second part, quite often with a graph, which usually involves some AC calculations. So just looking at the first part, you can see these are the 3 pictures for the last 3 exams. And in November 2018, you had an AC generator. You were told it was that. November 2019, it was a DC generator, but you were asked what type it was, and you could recognize that by the split ring commutator. And November 2020, you were asked what type of machine it was, and you had to state that it was a DC motor based on the fact that it had a split ring commutator and also a power source feeding electrical energy in. Now you can see in the picture there are slip rings there, a split ring commutator here. And again, in November 2020, you were asked to name part A, which you should know by now is a split ring commutator. Energy conversions, a generator is mechanical to electrical energy, even if it's a DC generator, mechanical to electrical energy. And in 2020, you were asked to name the energy conversion which takes place, and you should have been able to say it was from electrical, from the battery, to mechanical energy as the motor turned. Other questions you were asked, in 2018, you were asked for the current direction in the coil. 2019, you were asked to draw a voltage graph. And 2020, you were asked for the coil direction as the coil turned. We will look at all of those carefully. But notice there is this part 1 to the question, which really should be no problem for you to answer. Let's start with November 2018. You are given this picture here and various questions about the picture. So the first one says, in what direction does the induced current flow in the coil? You're told it's a generator, you're told it's an AC generator with the slip rings, and you're told that the coil is rotated clockwise. So that means the segment of wire XY is going to move upwards. Now remember, as we discussed before, you need to know Fleming's rules, and in this case, the right-hand rule, which is for generators, not the left-hand rule, which is for motors. So first of all, let's put in the different fields or forces. The magnetic field is always from north to south, just in the same direction as you see in the picture. Your motion will be in an upward motion because the coil is rotating clockwise. The direction of force is also upwards. So we have a very similar picture here to what we have in the picture of the hand. So therefore, the direction of the current, as you see here, will be in a forward direction. And so the answer is it will be from Y to X. Now, I've taken some time to explain that, but you see that's only 1 mark. So you need to practice this so you can answer that very quickly. Some other basic questions. On which principle or law is the working of the generator based? You could either say electromagnetic induction or Faraday's law or both of them. Again, just 1 mark. State the energy conversion. Well, with the generator, it's always mechanical to electrical energy. Very important. 10.2, the second half of the question with some of the AC calculations. You're given a graph of the voltage output for an AC generator. And first of all, you're asked to write down the maximum or peak output voltage. Now that's quite simple. You just read it off the graph, and that's 340 volts. If you said minus 340, you'd still get the mark because that's the peak negative voltage. Now they tell you a stove is connected to the generator and delivers an average power of 1600 watts. Calculate the RMS voltage delivered to the stove. Now, that's not difficult. VRMS, you should know from your data sheets. It's quite simple. Only 3 marks is Vmax over root 2. Vmax we get from the previous question. So it's 340 over root 2, which is 240.42 volts. 10.2.3, calculate the resistance of the stove. Well, we know that power from our data sheet is V squared over R. So we substitute in VRMS from the previous question, square it, divide by 1600, which is the power to get the resistance. Just change the subject of the formula, and we get an answer of 36.13 ohms. These were simple questions for 3 marks each, so I didn't bother to go through the whole progress method, but we will do it in the next example. Let's continue with the November 2019 question. Again, we've got a generator. They tell you a simplified diagram of an electric generator is shown below. And when the coil is rotated, an EMF is induced in the coil. 911, is this an AC or a DC generator? Well, you should be able to say quite easily it's DC because there's a split ring commutator. Now note, you didn't have to put split ring commutator. You didn't have to give a reason. I'm just giving that to help you. 912, briefly explain how EMF is generated. That is learning. It's induced as a result of change of magnetic flux linked with the coil. That's just learning work for you. Now you're asked to draw a sketch graph of the output voltage versus time for this generator and show one complete cycle. Now please don't forget that we've established that this is a DC generator. On page 62 in your books, we talked about this earlier in the video. You've got this comparison of DC and AC generators. Here we have the one on the left, the DC generator. So the output voltage graph looks like this. So here from the memo, these are the acceptable answers. You can either give a positive voltage or a negative voltage. I would suggest, again, you take the simplest graph and just take the first one. Notice one complete cycle involves 2 bumps on the graph, or if you start halfway through, it must go like this. Notice the allocation of marks. 1 mark for the correct shape, and the second mark for one complete cycle. Moving on to the equations question, we're told a 200 ohm resistor is connected to a DC voltage supply. Energy dissipated in 10 seconds is 500 joules. Then the same resistor is connected to an AC source, and 500 joules of energy is also dissipated in 10 seconds. Same resistor, same amount of energy. 921 is just learning work. That's a recall question I'll leave for you to do. 922 asks us to calculate the maximum or peak voltage of the AC source. Now this is 5 marks and it is a bit more complicated. So we're going to use the progress method, which you learned in video 6.1 to solve this. So progress method says we should start by drawing a picture. Now there is a picture given, but it's not really needed in this question. Then establish what is required. What are they asking? Now I've highlighted in green, they're asking for the maximum or peak voltage of the AC source, so for Vmax. There's no particularly obvious facts here, but what is given? 3 facts are given. Resistance is 200 ohms. The work done is 500 joules. And the time in which the work is done is 10 seconds. So we need to relate what is given to what is required. So we need to find Vmax, what is required, in terms of the 3 items that are given. To relate those, we need to find the correct equation from our data sheets. And in this case, we'll actually need 3 separate equations. And then, you know, SS stands for substitute and solve. So let's go to our data sheets. If you look on page 39, we have our alternating current equations. Don't confuse them with the normal electricity equations. And on page 38, we have the work, energy, and power equations. Now, we're going to use this one because you can see we've got resistance, and effectively those 2 figures give us power, and that will help us to find voltage. So we're going to find power from work and time over there using this equation from page 38. And then finally, to calculate the peak voltage or the maximum voltage, we're going to use this equation. So we actually need to use all 3 equations. So let's go ahead with 922. First of all, for the direct current voltage supply, we have power is equal to V squared over R. And power is also equal to work over time. So by equating these, we can say that V squared is resistance times work divided by delta time, by delta T, change in time. Resistance is 200, we were given that. Work is 500, we were given that. Time is 10 seconds. Putting the numbers in, we get V squared equals 10,000. Be careful, we still need the square root, which says voltage is 100 volts for the DC source. Now you know that that will be equivalent to VRMS for the AC source. So we can now proceed and say for the AC source, VRMS is Vmax over root 2. So putting in our answer of 100 volts is Vmax over root 2. So a quick calculation tells us Vmax is 100 times root 2, which is 141.42 volts. So follow through carefully how we use the 3 different equations to come to that answer. In the exams, the 5 marks are allocated as follows. First of all, 1 for getting these equations and relating them, 1 for substituting in the given values correctly, 1 for this equation for VRMS, 1 for substituting in the correct answer of 100 volts, and 1 for the final answer. This one was slightly more complicated, but I'm sure that you can do it if you just follow through the answer I've given you here. And finally, on page 65, the last of the question 9s, this is from November 2020. Again, it starts off with an electrical machine and a few basic questions about that. In this case, these questions actually count 6 marks, slightly more than usual. First of all, is this machine a DC motor or a DC generator? Now, we know it's DC because of the split ring commutator, but it's a motor because there's a power source putting energy in. 912, what is the energy conversion? Well, it's electrical to mechanical. The electrical energy from the battery goes in, and the coil turns and gives mechanical energy out. 913, write down the name of component A. I hope by now that you can recognize a split ring commutator. 914, in which direction will the coil rotate, clockwise or anti-clockwise? In this case, it'll be anti-clockwise. Let's do that carefully. First of all, we're going to use Fleming's left-hand rule for motors, and we're going to notice that the field goes from north to south. The current, because it's conventional current, goes from positive through to negative. Remember, conventional current is effectively flow of positive charge. And because of that, we can put those together, and we see that the thrust or the movement will be down. Now, you'll have to do this for yourself, but you have to take your left hand and essentially turn it around backwards like that to show the downward movement. And it's not going to look the same on the video. You need to try it for yourself. So that wire will move downwards, which tells you that the whole coil will move anti-clockwise. Now the second part, which has the alternating current calculation in it. We told the electrical device is marked 200 watts, 220 volts. The first part, again, is a straight recall question. It often comes up, so make sure you know it. We're asked to calculate resistance and energy. Now, again, here's the pages from the data sheet. We're going to need this familiar equation, power equals V squared over R. And from the work, energy, and power on page 38, power equals work over time. Now, this is not difficult to do. Calculate the resistance of the device. Average power equals VRMS squared over R. So we can rearrange that, put in our numbers, and say resistance is V squared over P. 220 is what we were given for the voltage. 200 we were given for the power. That gives us a resistance of 242 ohms. Not difficult. Now we're going to carry that value forward. You're asked, what is the energy dissipated in 10 minutes? Well, and sorry, this is when it's connected to a 150 volt source now. So we put in the new voltage, 150 volts as VRMS. We divide by the resistance we've just calculated, 242 ohms, and we get that average power is 92.975 watts. But the question said calculate the energy dissipated. So power equals work over time, so work equals power times time. So we simply multiply the power by 10 minutes and times 60 seconds per minute. Do that calculation carefully on your calculator, and we get an answer that the work done or the energy dissipated is 55,785.12 joules. So I hope this video has been helpful in getting you to understand electrodynamics and particularly to prepare for question 9. Remember, as I said, it is one of the easier questions compared with the earlier ones. So make sure you finish your paper and you get to answer question 9.